So, the discovery of fission. In the mid-1930s, Enrico Fermi was attempting to synthesize a new element by bombarding uranium with neutrons. The idea was that if you incorporated the neutron into the nucleus, it might undergo beta decay and convert a neutron into a proton and thus increase the atomic number of uranium, which at the time, well, and still is, that's the largest naturally occurring element, right? So he's wondering, well, could we make one with 93 protons? So he was trying to do this. So he did detect beta emission. So he did observe the electrons coming out, but he never chemically examined the product. So he didn't know if a new element was being formed or not. So one of the reasons we publish experiments results is so that other people can carry on, maybe where we left off, or check our work, make sure it's actually correct. So Meitner, Strassman, and Hahn repeated those experiments, and they found that the products were not heavier than uranium. There were several, and they were lighter than uranium. Not what was expected. This is a discovery that changed the world. So this was reported on January 6, 1939. Neutron bombardment of uranium resulted in nuclear fission, the splitting of the uranium atom, previously thought to be impossible. So the uranium atom split into a barium atom, a krypton atom, and 3 neutrons, and released an enormous amount of energy. So this is uranium-235 that does this. Less than 1% of the uranium in the Earth is uranium-235. 238 is the most common one, does not undergo fission. We had a question last week, and he's not here, but I already told him the answer, about why do thorium, protactinium, and uranium have such precise atomic masses when they are radioactive, and all the others are just a whole number in parentheses, which is, their mass number. So it was actually harder than I expected to find out. Those 3 elements have an isotope that is relatively stable, like, 100-year half-life or something like that. And so the mass up there is the mass of that one stable isotope. So interesting. All of these other naturally occurring radioactive elements, they have such short half-lives that finding the mass of them is just not really meaningful. So uranium-235, you bombard it with a neutron, and you get, that's the krypton. Yeah, that's the krypton, and this is the barium. And you get 3 more neutrons out and a lot of energy. And this is fission, which is splitting the atom. So if your sample has a lot of 235 in it, not just a regular sample that has less than 1%, but enriched, you can get a chain reaction going, where you get one uranium nucleus to you undergo fusion, the things fuse. If you undergo fission, do they fizz? I don't know. Split. If this splits and releases 3 neutrons, these 3 neutrons have the potential to induce fission in 3 more. And then those could induce fission in 3 more, and we get this chain reaction, and it's not just self-sustaining, it's like exponentially growing, right? So you need a critical mass of uranium-235 in order for this to be self-sustaining, but this reaction can be used to make an atomic bomb. Because this one splits, remember, not only are we getting these neutrons, we're getting a lot of energy. And so these go and split 3 more, and these, and it's every time increasing by a power of 3, I believe, right? Anyway, so this is an interesting letter. I'm going to read it to you because I think it's so interesting. This is a letter from Albert Einstein to President Roosevelt. And he wrote this letter at the persuasion of a lot of U.S. scientists who were afraid that Nazi Germany would develop a bomb based on nuclear fission. Sir, some recent work by E. Fermi and L. Szilard, which has been communicated to me in manuscript, leads me to expect that the element uranium may be turned into a new and important source of energy in the immediate future. Certain aspects of the situation which has arisen seem to call for watchfulness and, if necessary, quick action on the part of the administration. I believe, therefore, that it is my duty to bring to your attention the following facts and recommendations. In the course of the last 4 months, it has been made probable through the work of Joliet in France, as well as Fermi and Szilard in America, that it may be possible to set up a nuclear chain reaction in a large mass of uranium, by which vast amounts of power and large quantities of new radium-like elements would be generated. Now it appears almost certain that this could be achieved in the immediate future. This new phenomenon would also lead to the construction of bombs, and it is conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed. A single bomb of this type, carried by boat and exploded in a port, might very well destroy the whole port together with some of the surrounding territory. However, such bombs might very well prove to be too heavy for transportation by air. It's a really interesting piece of history. So that was in August of 39, and in 1941, the Manhattan Project began. I was in Los Alamos, New Mexico. And the goal was build an atomic bomb before Germany does. So the first nuclear weapon was detonated in 1945, 4 years later, at a test site in New Mexico. This is not a picture of the actual first nuclear weapon, but it looked like this. Had a force equivalent to 18,000 tons of dynamite. So by this time, Germany had already surrendered, but the U.S. dropped 2 bombs on Japan, killing 200,000 people. And of course, the development of this bomb really changed warfare and led to things like the Cold War with Russia, where we're fighting but we're not fighting. And then it's interesting to watch, Russia is trying to take over Ukraine right now. And they could pull out nuclear weapons, right? And just get it over real fast, except then what would happen? We would go after them with our nuclear weapons, and that would be kind of a chain reaction, and we'd probably destroy the earth and all humanity, right? And so it's this tense situation where you want to stop somebody, but how much force do you use? And it's a very interesting situation, and tragic too. So what about using this for good? So a controlled fission reaction would generate electricity with no air pollution and would produce no greenhouse gases. This would be awesome. Nuclear fission generates about 20% of U.S. electricity, up to 70% of electricity in some countries. A pencil-sized cylinder of uranium could power a typical car for 20 years. A coal-burning power plant uses 2 million kilograms of fuel to generate the same power as 50 kilograms of fuel in a nuclear plant. But why aren't we using more nuclear power?
It's not common, it's expensive.
Well, the problem is nuclear accidents and waste disposal, and a lot of public opinion as well. People are afraid of nuclear reactors. Not in my backyard, right? So how does a nuclear power plant work? This is a simple illustration. So here we have the reactor, and we've got the uranium in here. We've got the uranium fuel rods, and they are interspersed with retractable neutron absorbing control rods. And the idea here is that if the reaction starts going too fast, you'll lower the control rods and absorb some of those neutrons and slow things down a little bit. And so you can keep control of it in this way. So this is generating a lot of energy, a lot of heat. And so we've got water coming through here, and it's superheated, pressurized water. And that is used to heat another tank of water. So this water is separate from the water that's involved with the actual radiation. Two separate sources of water. And so the steam from this can be used to turn a turbine and generate electricity. Anybody have any questions?
So
Yeah.
the neutron were to hit the uranium, it causes nuclear explosion?
Well, it doesn't cause a nuclear explosion if one neutron hits one uranium atom. So that event releases a lot of energy, but is not an explosion. Where it becomes an explosion is when this is, you've got 1, and then you've got 3, and then you've got 9, and then you've got 27, and it's getting really big really fast. And so then you've got your explosion. So here they can keep it under control, self-sustaining, but not out of control exploding.
What is the waste?
What is the waste? Well, some of it is the spent fuel rods. After they no longer have enough uranium-235 in them to produce energy anymore, then what do you do with them? They're still radioactive.
So the explosion happens as the chain reaction is expanding.
If the chain reaction is allowed to go without being slowed down by anything, it will explode, yeah. So the biggest problem is the danger of nuclear accidents. So there are safety precautions, but accidents can still happen. A notable example is Chernobyl, 1986. So they were doing an experiment that was designed to reduce maintenance costs. So they had disabled some safety features, right? We want to save a few pennies on maintaining this thing, so we're going to do this thing.
It got destroyed.
It got destroyed. And 32-kilometer radius became uninhabitable and is still uninhabitable. Yeah. Chernobyl, there's people, you can't live there still. So what happened is the nuclear core was part graphite, and as it overheated, it began to burn, and huge explosion. Amazingly, only 31 people died immediately. It's really hard to tell how many died as a result of that, because radiation sickness, you don't know what, and like cancers and things, you don't know if it was caused by this or it was coincidental. So, and then in 2011, which you guys might be old enough to remember, Fukushima, Japan, there was a 9.0 magnitude earthquake. The earthquake didn't cause a problem, but the tsunami triggered by the earthquake caused a problem, in that the cooling system pumps failed because they got flooded. So they've got cooling ponds, and they cool the water, and they pump it back in, and you've got to keep this water flowing to keep things under control. And they had backup generators and stuff. They were prepared for power outage. That was fine. What they didn't anticipate was all the debris that came from the tsunami tidal wave and clogged up the pumps. And so 3 of the nuclear cores overheated. There was a partial meltdown. There was significant radiation release, but it was much, much lower than at Chernobyl, and no radioactivity related deaths. So what's important to understand is neither of these tragedies, accidents, was a nuclear detonation, because the uranium fuel used in the fuel rods does not have enough uranium-235 to do that. Can't detonate. But it can get hot enough that it melts down. So, of course, we have learned from previous accidents, and safety features are employed. And I think probably one of the rules is don't turn off the safety features. But again, there's, who could anticipate a tidal wave? I mean, it's not like they built this thing on the coast, right? It just, really, really freak act of nature. Anyway, anybody have any questions about, well, I guess we could talk about this for a minute. So the other problem is nuclear waste. Some of the products, so the uranium-235 breaks into krypton and barium, and those products are radioactive. And so when you're done, you have some radioactive material that you need to dispose of. Those things have long half-lives, and so you can't just, we'll just wait till they fizzle out. Yeah, thousands of years later. So currently, nuclear waste is stored at the power plants in the U.S. They were going to make a single disposal plant in Yucca Mountain, Nevada, but work on that stopped back in 2010. And things are just kind of stalled out on that. Because, of course, nobody wants nuclear waste, right, around them. Committees made recommendations, no decisions.
Is there a way to speed up the half-life?
No, there's no way to speed up a half-life. It is what it is. Any other questions?